All right, we are recording, and today we have a special guest. Would you like to introduce yourself?
Sure. So hello, everyone. My name is Mr. Culver. I am the Diversity and Inclusion Instructional Coordinator here at Blair, previously the RT or Chair over the Social Studies Department. For those who do not know me, I am a Blair alumnus myself. So I graduated from Blair a couple decades ago. So it is nice to be back with the community for the last several years teaching and learning with you guys.
Awesome, thank you. So we've been hyping you up, and we wanted to just bring you in and ask you a couple questions that we've been asking the students as well, some icebreakers.
All right.
So without further ado, what is your favorite pizza topping?
My favorite pizza topping, believe it or not, is mushrooms. And a lot of people hate them. I love them. So I make my kids
old, Mr. Culver.
Yes, I know. I make my kids so upset when I get mushrooms on the pizza. But I admit that that's my weakness.
At least it's not anchovies.
Exactly.
I've never had anchovies on pizza.
Oh, I had anchovies when I was a kid. Tuesday night pizza night. It was $5 pizza night at the place on Aspen Hill Road. Oh my gosh. Anchovies and cheese, because my dad's a vegetarian. All right, we got some more. What is your favorite cereal?
Cereal. When I was a kid, I love two. I love Captain Crunch and I love Apple Jacks. And Captain Crunch, for those who know, if you're a fan, you got to eat it like within the first 5 minutes. After that, it gets soggy and it's disgusting. You got to throw it out. But yes, I love my Captain Crunch. I got to eat like half of a box in one sitting if my parents let me.
Oh, man.
Cereal.
All right, segueing from sugar, let's go to more sugar. What's your favorite ice cream?
Ice cream, cookies and cream all day. Love my
that's
Oreos and my vanilla ice cream, no doubt.
I believe that's what I said too. Although I like vanilla ice cream, you can pour the chocolate syrup on top.
Yep, exactly.
I think it's like the perfect add things to it ice cream.
There you go. Absolutely.
Wait, Grace, what's your favorite ice cream?
The Oreos with coffee ice cream. So it's like coffee Oreo combination.
See, that even better.
Next question. What is your favorite fall food?
Fall food. I love Starbucks pumpkin lattes. So you know it's fall. Bring that out. And I usually don't like pumpkin stuff, but something about their pumpkin coffee gets me. So yeah, I love.
You don't generally like pumpkin stuff, Mr. Culver?
Like what else is there to eat? Well, I'm not gonna eat it like in a stew or
just eat it out of the top.
Yeah, just open the can.
Like pumpkin pie is okay, but I'm a sweet potato pie kind of guy.
Right, I respect that. I make these pumpkin steamed buns, and they are delicious.
So I have to try
back in real life school. I'll bring you some.
Exactly. Yeah, you taught me something new. I'll reserve judgment.
Grace, this is why we're learning to plank for 5 minutes and running for 100 miles in October. So
we're ready to eat all this again. We can eat Mr. Kirk's bread. We can eat pumpkin buns.
There you go.
With our pumpkin spice lattes.
Yeah, absolutely.
All right, we got one last for you. And this one's a tough one. You might have to think. Do you have a math joke?
So I have a math joke. I'm going to cheat a little bit. I was given a little bit of cliff notes. I said, prepare for this by coming up with a cool math joke. So I found one that I think is nice and appropriately cheesy. So what are 10 things you can always count on?
What?
Your fingers. All right, see, I gotta laugh at somebody, so that's the mission accomplished.
The best thing about a math joke is they're not funny at the core, but you never know what the punchline's gonna be.
Exactly.
Always a curveball. All right, but we can count on you. Thanks for swinging by. Very much appreciated. We're gonna jump into inverse functions. You're free to stick around, but you're a busy person. But can the students come and talk to you if they need you ever?
Anytime. So
awesome.
Again, my whole mission in this position is to make sure we're providing a supportive environment and an outlet for students whenever they have concerns about, equity in the classroom, if they feel uncomfortable with something that's said, or there's a dialogue that they felt was marginalizing or somehow felt invalidating, then they can reach out to me directly. You guys can reach out to me directly via email, and I'll be happy to kind of provide a forum for you guys to kind of talk through what we can do so that those things don't occur, over and over again. So thank you for the invitation, Mr. Kirk and Ms. Contreras.
Thanks for
Awesome.
coming, Mr. Culver.
Yeah. All right, let's jump into some math.
All right.
Let's start talking about functions, inverse functions to be exact. Let me go ahead and title my page. So over.
So actually, Mr. Kirk, I think it would be good if we took a moment to confront some of the things that I've noticed in some of the videos that we've been doing. That I feel like a lot of times I feel like you're talking over me, and I feel like that kind of that I feel that invalidates what I can bring to the table. So I just wanted to challenge that behavior and address it so that we can move forward in a productive way. What do you think?
I'm sorry that I've been doing that. Absolutely. Thank you for pointing that out. What do you think? How can we proceed? Yeah.
Well, I think that if maybe you could just be a little bit more aware of, when I'm giving you like visual signals that I would like to say something. I think that would help. And I know that you have 2 monitors, so maybe like having it so that, you can see me a little better in the setup. That I think that's an adjustment that I think you could make. And I think just moving forward that we can really we can go from this into something that's productive, where both of our knowledge and both of our experience and both of our ideas can really be heard. What do you think of that?
I just did it. Sorry. No, I've moved my monitor. Very, very simple change that I can do. I absolutely want your voice to be heard. And the fact that I've been talking over you, that's not cool at all. Thank you so much for confronting me. I really appreciate that. Yeah,
And just to
let's do this.
Just to be clear about because we did use the word confrontation. We do want to think of confrontation as something that isn't necessarily a bad thing, because I think a lot of times, like in our culture and our language, that like confrontation has this very negative connotation. But I mean, if we think of confrontation as something where we're challenging a problematic behavior, or we're addressing something that we want to be made better, that it's okay to have confrontation.
Yeah, and once again, thank you for confronting me. I think that this is something I need to work on. I don't think it's just with you. I think just it's something that I interrupt people, and I'm leveraging a power that I have as a white male. So this is something that I want to move forward, thinking about and incorporating into my lifestyle. I'm going to and tell me if this is satisfactory to you. I've moved my computer screen so I can see you a little bit better as I write. But I will try to do a better job scanning back and forth and looking for those visual cues from you. Is that something that we can do?
Yeah, I think that sounds good. And I think also just giving the space to say things like, well, Ms. Contreras, what do you think? And just taking those pauses and those moments. And that's something that I think could be really helpful in this collaboration environment that we're in.
Yeah, I will definitely try to check in more, and use those words and maybe even some wait time if necessary. Sweet. I think that's a plan. Hey, if it doesn't work, this is something that I want to invest into. But if it doesn't work, if I still have issues, Can we move forward with some other thing that might help me improve?
Yeah, I think that is something that we can definitely do. But we can just see how this goes and address it again if it's still an issue.
And then please confront me if it's still an issue.
Sounds good.
Awesome. Are you ready to get started?
Ready.
Let's do it. All right. So just going to type my page. What is the date? Today is today. And the period is some natural number. I'm not going to put a plus this time.
It's reasonable.
All right. So we are looking at inverse functions. I have two sets here. Can you help me turn this into a function?
Well, I see that we have A is 1, 2, 3, and 4, and then B is 5, 6, 7, 8, which to me that just looks like we're taking our value in A, and then we can just add 4 to it, and then we'll get our value for B, all our values for B. So yes, the good old bubble diagram.
Yeah.
Love it.
Wait, so before I do that bubble diagram, let me write exactly what you said. We have a function f, and it's taking values from A to B. And you said the function rule was x plus 4. I think it's good to write those down. Let's get that old-fashioned bubble diagram going. We have 1, 2, 3, 4. And we have, that looks like a potato. 5, 6, 7, 8. Right.
Potatoes come in all sorts of shapes and sizes.
That is true. I have some wonderful, speaking of fall foods, we have some sweet potatoes over there, and they're like the weirdest shapes. All right, so this problem, it never really told us what one was going to, but you've constructed a function here. You have, I guess, arbitrarily decided that the function is x plus 4, and 1 is going to 5, which is perfectly fine. My question to you is, what if I want a function that takes 5 back to 1? What if I want to invert this operation, this function?
Invert. So you want to go from B to map back to A. So I think that all we need to do is, instead of adding 4 to our set A, we just need to subtract 4 from our set B.
So I'm going to write, it in a very specific way. X minus 4. 5 goes to 1. 6 goes to 2. 7 to 3, and 8 to 4. I didn't mess anything up there, did I?
That looks good. I think back in your set B for F, the 8 doesn't look like an 8. It looks like a 5. Okay.
Problem solved. Right. This is a function that reverses the operation of the previous function. And that is what this lesson is all about. We are going to be talking about what we call the inverse function. It is a function that reverses the operation of another function.
How do we read that with the f and the -1 in the exponent? How are we supposed to say that?
That's a good question. So it is not implying that we talked about exponent rules back way back when, and like a to the -1. We had defined that as 1 over a. I think this is a good moment to describe that this -1 is not an exponent. It's not an exponent. If I wanted to write it as an exponent, I would have instead wrote it on the outside of the function. Hopefully our heads aren't covering this up and I can't scroll down. Oh, I can a little bit. This is 1 over f of x, right? But this is a different symbol. Right? This symbol, the way we read it is we say f inverse of x. F inverse of x. And it is a completely separate function. Very often, not the reciprocal. Oh, I don't know what that was. Very often, not the reciprocal. I think it has to do with the fact that I'm right on the.
I think you can scroll sideways a little bit. There it is.
Yeah, I can. Full width lied to me. It is less than full width. All right. But that is what an inverse function does. It takes the original value back. So I want to go ahead down here. I'm going to change my color so I can differentiate it from the purple. Let's go with blue. I want to write the definition of an inverse function, which I've written down here. Oh wait, no, but I think there's a better way to get this.
Oh yeah, definitions. Those tend to be things that we can find in books.
I don't want to read my terrible handwriting. Let's go ahead and get to the textbook. And I've placed the textbook, and I recommend everyone do this. I got a bunch of things up here. All right, and all you got to do is on a web page, hit the star right here. All right, but I have teacher view. I have Slack. That's how Mrs. Contreras and I communicate. I have Discord. That's how another teacher and I communicate, Mr. Schwartz. I got Canvas because obviously we're going to Canvas a lot. Remind, Zoom, the Bell schedule. That is more useful this year than usual. I've got some band apps from the marching band that I help with. Curriculum stuff, PDF to image. Let's just like open that one real quick. This web page takes your PDFs and converts them into images. If you ever want to utilize that to like upload things to Kami. Let me go back though. But there it is, OpenStax. Let me open in a new tab. Let me scroll myself down. Free, open, accessible. With your help, give today. Should probably give. View. I want to view online, right?
View online. Don't
Awesome.
download it. It's not
Right.
worth it.
So should I go through this textbook and try to find the word inverse?
Well, so that is one option. I think that there is also a search this book, and then you can just type in inverse and see what happens.
I spelled it right? Boom. Cool. All right, so we got the first chapter.
3.7.
3.7. There we go. Inverse, that is what we're doing. Right, there's lots of inverse stuff before 3.7, but we are looking at 3.7. Learning objectives. We can go through this. We could like utilize this to help us write lessons. Putting functions in. Oh, look at that. Putting y in, getting out x. We've talked about this.
Whoa.
Go down a little bit.
Oh, look, it's in Celsius. Isn't
Oh,
that like your favorite, Mr. Kirk?
Oh, I like Kelvin. All right, there it is. There's the definition. Definitions often in textbooks. This is not like a set in stone rule, but it's kind of happens a lot. Definitions are going to be found in like those boxes. So we got a box here, inverse functions. Then we get some examples. This might help you if after this lesson you still want a little bit more help with inverses. Go to the textbook, put it in your saved locations with the star button, and then check this out later. But here we go. And I wonder if I can make this a little bit bigger.
Yeah, it's rather small. Maybe closing the sidebar.
Control 0 gets me back to 100. Close the sidebar. Nice. Oh, I just opened it back up. There we go. Can you see that a little bit better?
Nice.
All right, cool. So would you mind reading this for us?
Sure. For any one-to-one function, I wonder if that's important. One-to-one function, f of x equals y. A function f inverse of x is an inverse function of f if f inverse of y equals x. This can also be written as f inverse of f of x, which equals x, for all x in the domain of f. It also follows that f of f inverse of x equals x for all x in the domain of f inverse if f inverse is the inverse of f. The notation f inverse is read f inverse. Like any other function, we can use any variable name as the input for f inverse, so we often write f inverse of x, which we read as f inverse of x, and keep in mind that f inverse of x is not equal to the reciprocal of f of x, and not all functions have inverses.
I think that last thing you said there, not all functions have inverses, takes us back to some of the first words you said, one-to-one. Let me go back to our lesson. This function I gave you, it's one-to-one. 1 goes to 5, 2 goes to 6, 3 goes to 7, 4 goes to 8. What happens if it wasn't one-to-one?
Well, then we would have multiple arrows pointing to numbers, right? that we would have like 1 pointing to 5 and 2 pointing to 5, maybe.
Let me give myself a function real quick. If 1 goes to 1 goes to 2 and 2 goes to 2. I'm just making this up on the spot. All right, the inverse of this takes 2 back to 1 and back to 2.
And then that's not a function.
It's not a function. So it is a requirement that functions be 1-to-1. But if a function's 1-to-1, then it's going to have an inverse. There was another thing in that definition I think is really important. Right? It wrote that f of f inverse of x is x. Can you talk on that a little bit? Why does that make sense?
Well, because x is just the identity function. So we have like identity in terms of the identity property of addition. When we add 0, we're changing nothing, right? When we have the identity property of multiplication, when we multiply by 1, we're changing nothing in our output. So if we have an identity function, that idea is that when we're taking our function, we're changing nothing between our input and our output. So our output is always just going to be exactly what our input was. And that is identity. So if we have f of f inverse of x spitting out the identity function, that means that we're just changing nothing as long as we're composing those functions properly. And I think it also had f inverse of f of x equal to the identity function x. And having that reversibility of what the composition would be, I think that's also important because we did have in our last lesson, we had some functions where f of g of x equals, we had f of g of x not equal to g of f of x, right? So not all compositions give you the exact same thing.
All right, in general, f of g does not equal g of f. But you're telling me, you're telling me that when you compose inverse functions, you get x, regardless of the directionality. I do not think directionality is a word, but let's pretend it is.
It's fine.
See, and I think like we've said a lot about inverses, and we have that formal definition in the textbook, written better than I could ever write. But the things that I think we need to take away are that when you compose inverse functions, you get x. And the purpose of an inverse function is to take the range back to the domain. And then finally, it needs to be 1-to-1. If it's not 1-to-1, then we're going to get a non-function as the inverse function, which is like explosion. Doesn't make sense. Brain does not compute. Cool. All right, so that is what a inverse function is. Let's find some inverse functions. There's plenty of ways to find an inverse function, many strategies. I have a function here, f of x, 2x minus 6. So if I plug in like 5, that is going to go to, and actually let me write this in a much more maybe intelligent way. I don't know. F of 5.
Organized. I think a more organized way.
Yeah. What's that going to output?
That's 2 times 5 minus 6. So with order of operations, right, we do the multiplication first. So we have 2 times 5 is 10, and then minus 6 is 4.
So we need a function that takes in 4 and outputs 5. Any ideas of how we can find this function?
Well, the way that we got 5 mapping to 4 with f of x was that we multiplied by 2, and then we subtracted 6. So if we do those operations in reverse, so we add 6, and then we divide by 2, then we're effectively undoing the operations that we did in f of x.
Let me just get what you said written down. multiply by 2, then minus 6, plus 6, then divide by 2. All right, so what's that going to look like for the inverse function?
So f inverse of x would be x plus 6 and then all over 2.
All right. I am skeptical. So what I can do to check your answer is I'm gonna use the definition of an inverse function. I'm gonna compose these two things, and then I need to get x. So I'm gonna bleed into the space for b, but we'll address that in a second. Actually, I really don't want to, so I'm gonna go over here. I'm over here now, and I'm gonna compose these two functions. So f of f inverse of x is equal to.
Lost a parenthesis there.
Yeah, I got you. So I'm composing, so I need to take the function 2x minus 6 and then replace x with x plus 6 over 2. All right, does this give me the function x?
Yeah, because when you multiply by 2, you get x plus 6, pew pew. And
Pew,
then x plus 6 minus 6, you get x.
Right. We got the identity function. Does it work both ways?
Oh, let's check.
Let's check. Man, I just not enough room for the size I've written things. What do I want to do? I'm just gonna do it over here. All right, so f inverse of f of x equals. So I'm gonna take your function x plus 6 divided by 2. I'm gonna put a 2x minus 6 there. Zoom, zoom.
Whoa. It's x.
Probably, it's x. Boom. All right, so we have found the function. Right, and you know what? I think I'm going to leave b as an example. Are you okay with leaving b as an example for the student?
Oh yeah, I think they can handle that.
Because there's one last thing I want to do with a, and I need the space. So that's kind of the reason.
It's like very selfish.
Very selfish reason.
As an example.
All right. What was that last thing I wanted to do with a? Oh, there is another way to find inverse functions.
Mm.
And it kind of takes in the essence of what an inverse function is. Right? You plug in x, you get out y. We want to plug in y and get out x. So let's just do that. Let's take our function, y equals 2x minus 6, and let's do a little switchy. What do we call it? The flippy? Let's do a little bit of flippy.
I don't know if we have a name for that.
I think when we multiply by the reciprocal of the denominator, did we call it flippy?
Yeah, we call that flippy, but that's different from what we're doing. We're like changing variables.
This will be switchy. All right, so x outputs y, so now we want y to output x. So I'm here, and then what was the first operation you said we needed to do to reverse the operation?
We said plus 6, right? It's kind of right there. Yeah.
Yeah. So I'm gonna do exactly that. I'm gonna add 6.
Oh, wild.
X plus 6 is equal to 2y. Then what did you say?
And then I said divide by 2.
So
pew pew.
What you said earlier is essentially what I've done here. If I switch x and y and then solve, I am doing all the operations in the reverse order. Thus, let me get this in a new color so it pops. Y is equal to x plus 6 divided by 2.
Hey, that's exactly what we had for f inverse. It's like right there. Right.
Big old equal sign.
Right there.
Cool. So we have two methods for solving, or not solving, but for finding inverses. Think about the order, the operations in the reverse order, or switch x and y. I actually like x and y better because it kind of does the thinking for you. I didn't need to think about plus 6 and then divided by 2 because that's just what I did. What are your opinions?
I think it's choose your own adventure kind of thing. When you're like, if it's easier to think about it in one way, like switching the operations, then it's great. But I think that I tend to like doing the reversing the x and the y when it just looks a little bit more complicated. It feels a little more dangerous just trying to do it by writing down the order of operations. Well, you have a lot of practice with algebra, so you can trust the algebra.
going off of what you're saying, I have something a little bit more complicated.
Hmm.
We have a function f of x is equal to 6 over x plus 3. Now, this is a multiple choice question, right? But it's not like a test multiple choice question where your job is to just find the answer and move on. I want you to think about these two answers. And I want you to think about, why would someone put that as the answer? Why is that the other multiple choice? Let's look at both of these answers individually and try to understand why they are there in the first place. One of them is correct, one of them is incorrect.
I think A. I think A is addressing the that misconception that we might have from the notation, where we were talking about before that f inverse of x. It looks like you would have f of x and then the reciprocal of it because of our exponent properties, but it's not. It's not that.
It is not.
So A is showing that that we don't want to use that reciprocal as our inverse function. Because I mean, if you plug that in, right? If you compose f of g of x, what are you gonna get? Something totally crazy.
And we could do it.
We could leave it as an exercise for the viewer.
That's true. Yeah. I think another cool exercise for the viewer is, we've just said that this is not true. But I wonder if it's possible that it is true in some cases. In general, this is not true. The inverse is not the reciprocal. But I wonder if the inverse is the reciprocal in like a very special case. That's a journal entry, I think.
Or something we're going to talk about further on down in the doc.
All right. So you cancel out A. So by the rule of multiple choice, B is the answer. But can we like just real quick verify that it's the answer?
We should verify. How do we verify? Do we want to compose f of h of x, or do we want to compose h of f of x, or do we just want to do our switchy and do x and y switched in our f of x or h of x? Actually, there's a lot of options. Choose your own adventure.
Right? I don't know. What are you feeling?
I'm feeling switchy.
Switchy.
Yeah.
So x is equal to 6. Oh wait. Is it okay if I switchy the answer and get the thing given to me?
Yeah. Totally fine. So then what we get x plus 3 equals 6 over y. And then what do we want to like show it very carefully, or do we just want to flip the y and the x plus 3?
I think we want to exemplify the fact that we care about showing work, because that is something that we should address just real quick. Is that's something that we very much care about, not only because it's incredibly important and in normal school we care about it, but I mean, we're online, and since there's a little bit of difficulty in seeing your understanding, we can't like look at what you're doing. Seeing all of your work, I think, is imperative normally, but also especially now in the online environment. So let's do each step.
What if like showing it is really hard and you like would rather just like use your words and say it? Is there like a tool that we can use in Kami that can like capture our audio bites?
I think so, right? Comment.
Mm-hmm.
And then we have the ability to use this when we leave feedback, but you have the ability to use this if that's what you want to do to share your thought process, right? We don't want just the answer, but what we do want to give everyone the ability to show their work in a way that works for them. So I guess we could do that right here. I think I'm recording right now. Look, I'm recording right now. Awesome. What do we need to do? I think. Do you mind if I do this since I'm recording it? All right, so I'm going to multiply both sides by y. And I'm actually going to write down what I'm doing as I'm talking. Multiply both sides by y. And then divide both sides by x plus 3. And my final answer is x plus 3. And look, that is what we were given. Let me go back over here and stop my recording. And
Nice. Oh, is it recording again or is it playing?
No, it was playing.
Oh, I couldn't hear it. Maybe
Oh,
it
you
was
couldn't
only
hear
in
it?
the headphones.
I hope that it was picked up. Oh, I'm not sharing my computer audio, so it may have not been picked up. Sorry, everyone, for that 16 seconds of silence. If it was there, hopefully it wasn't. I can always go back and post and add it. All right, but yeah, you recording your solution is a valid way to solve these problems. But we do want to know the process that's in your head. If that means taking what's in your head and putting it down on a page, cool. If it means taking what's in your head and saying it, that's okay. That's okay too. Thank you for bringing that up. All right, so we got the answer. We're spending a lot of time on these problems because there's a lot to talk about with inverses. And we got a little bit more we need to get to. I got two functions for you here.
Those are parent functions. We know how to graph those.
Those are parent functions. Cool, let's graph them.
So for A, f of x equals x cubed. Yeah, you got 0, 0, 1, 1, 2, 8. Negatives. Yep, just like that. And then we want to be very careful when we're graphing this, though. Yes, nice.
Yeah. And we keep saying this, and the reason why is coming. All right, there's another function that looks very similar to this that we want to differentiate.
Differentiate.
Right, math jokes. All right, not as good as Mr. Culver's math joke though.
That was really good.
We got the square root of x. What's that going to be?
The cube root of x.
Cube root of x. Sorry. Thank you.
So we're going to do 0, 0, 1, 1, 8, 2, negative 1, negative 1, negative 8, negative 2. Nice.
Always could be better, but don't forget that this is with my hand, and it's not a computer. Computer is always going to be the best. Cool. So we got these two functions. Do you notice anything jumping out?
So we have our function. Let's see. Is this a good approximation for?
From my point of view, yes.
All right. So when we have x cubed like that, when we're going from x cubed to cube root, I think we're doing something like that. So it's not just like a straight like rotation that we're doing. We're actually, it looks like we're doing a reflection. This is really hard in the mirror.
Yeah, there is a reflection happening here. But let's backtrack a little bit. Look at the two functions we have: x cubed and the cube root of x. There is something that we have not said about these two functions, that it's true, that obviously pertains to this lesson. What happens when I compose them?
You get out x.
Right? Let me scroll down a little bit. I got a little bit of room, right? If I take the square, I keep saying it, the cube root of x, and I cube it, right? I get x. Right? The square root of x and squaring, I get absolute value of x, but that's not this problem. I get x. And if I do the other way around, if I do x cubed, the cube root, I get x. What does that say about these two functions?
Oh, wait, this is like our definition of our inverse function. That means that f of x and g of x are inverses of one another. That g of x is f inverse of x, and f of x is g inverse of x.
All right. While they've been named f and g, they are inverses. These functions are inverses. And then you made a really powerful statement earlier that I want you to repeat, if you don't mind. What was that?
I'm trying to read your mind and I don't remember.
Oh, it was about the graphs. You were doing this thing.
Oh, yeah. So when we're looking at these graphs and we're thinking about the relationship between them, we're getting a reflection, not a rotation. And the reflection, I think, is something very special.
Let's go to the next page, and let's graph these two things on top of each other. I need to zoom out for this because in a normal world I want this really big on the page, but with Kami we need to zoom out a little bit. So just like so everyone can see the prompt, I'm asking to graph f of x and g of x on top of each other. I'm going to do them in different colors. I'll make the first one blue and the second one red. Let me graph them real quick. So just give me 1 second. And this might have actually been a good time to pull up Desmos and then the power of Desmos, but I'm going to stick with what I've done here. Next time, we'll use Desmos. I totally missed that point, but you know what? The law of large points. Let's make that.
Is that a thing?
Shh.
There's also the eraser tool, but you know.
All right, and then 0, 0, 1, 1, 2, 8. Sorry, 8, 2.
8, 2, yeah.
8, -2.
Okay, so 0, 0, 1, 1, and -1, -1, those didn't change. But
Right, these are
everything else changed. This looks like it's a reflection across, wait, this looks like it's a reflection across the line. Ooh, and in purple, love it.
purple, purple,
This is some color theory going on.
right?
So we're going across this line, x equals y, y equals x, our identity function.
Y equals x, the identity function. It plays a massive role in what inverse functions, like all the properties of inverse functions. Right? If I look at this blue function here, up here, that's 2, 8. Down here, that's 8, 2. I should have put that in red, but whatever. I'm not going to backtrack. Right? When I want to graph the inverse function, what do I got to do?
It's just switchy. You're switching the x and the y coordinates.
Conclusion: to graph inverse functions, simply switch. Should I write that?
No.
Switch x and y. Right, x comma y, and this is some geometry notation that you guys might have seen last year. Y comma x, and if you think back, that was a reflection over the line y equals x. This is a reflection over y equals x.
Woo!
Can you summarize some of the really important points on inverse functions?
So with our inverse functions, if we're looking at it algebraically, if we want to go from our function to our inverse function, we switch our x and our y, and then we solve for the y. When we're taking our inverse function and we're composing it with our original function, so f inverse of f of x, we get out our identity function. And when we're looking at it graphically, when we have our inverse function, it is a reflection of our original function over the line y equals x. And the way that we can also get those coordinates is by switching our x and our y. There's a lot of switching happening.
Switchy. That's why we say it twice and with y's. Switchy. It's really important. That is a lot of information, but I think that's a good thing. Like the more information we have on an idea, I think the easier it becomes. Let's apply some of this knowledge. I got 2 functions for you here.
Can we make it bigger?
Yeah, we can. Yeah, let's go back to full width. Good call. Boom. All right, so the prompt, graph f of x, and then I want you to graph f prime of x. And I'm actually going to add a
inverse of x. Whoa, Mr. Kirk, getting all calculus up in here.
Then I'm going to graph f inverse of x, and then I'm going to add a third thing. What is f inverse of x? I want the rule too. I'm going to add that after the fact. All right, so show me the ropes.
Well, we have a parent function that's being transformed. We have root x, which we know it looks like something like that. Oh,
like a diver.
Okay. And then it's being translated to the right by 3 units. Why is it going to the right, Mr. Kirk?
Why is it going to the right? Because the things that we can plug in now are things 3 and bigger. Before we could go from 0 to infinity. But now when we plug in 0, we got a problem. We need to up that. We need to go in the positive direction, 3, so that the function accepts it. So 3 is now going to give me 0. 4 is now going to give me 1. What's the next one? 9? No.
8.
8 is going to
No.
give me 3.
7. 7. 7 is going to give you 2.
7's going to give me 2. I don't know why that was so difficult.
Good morning.
We should have just gone over 4 up 2. That would have been smarter. All right, and this is a function, so it's going to continue. This is not. It has a restricted domain, 0 to infinity, but it has no right terminal point. This keeps going. All right, cool. So there's our function. You've done A.
And then
How do you-
we should probably change colors for f inverse of
I agree.
x. And we just need to switch our coordinates and like reflect it so that we get what is that? 0, 3. 4, 1. No.
4,
No.
1 becomes
1, 4.
4.
Whew. And then what did we say that was? Oh yeah.
3, 4, 5, 6, 7, 2.
7, 2. 2,
Becomes
7.
2, 4, 5, 6, 7. And that'll be enough to get the shape. Boom. But that is in fact a reflection over the line y equals x. Bingo. Cool. And then
Cool.
what is this function?
So to get that, this feels very dangerous because we have a square root. Because I know that when we square things, we get parabolas. Well, let's just do it anyway.
Okay.
So y squared equals x minus 3.
Well, before we do that, let's do the first step, right? Switchy, switchy.
Switchy, switchy.
Yeah.
X squared equals y minus 3. And then add 3 on both sides, we got x squared plus 3. But
Wait.
we only want, because the red function that we have, which is our inverse function, is only defined on the domain from 0 to infinity.
Let me do this. F of I want to do blue. F of x. You said the domain is 3 to infinity?
3 to infinity. And the range is from 0 to infinity, including 0.
So what's the purpose of the inverse function?
We're taking our domain and our range and we're switching them. Switchy, switchy.
Yes. The purpose of the inverse function is to take the range back to the domain. So the inverse function, I think by definition, should have a domain that is the same as the range and a range that is the same as the original domain, which is the case that we have here, right?
Can I just point out that I really appreciate that you did the infinities in that way and you didn't even complain about it. Good job, Mr. Kirk.
I'm only doing it for you guys. But I do math on my own paper. My infinities are little sunglasses. Not sunglasses, but like Harry Potter glasses. So I think it's finding the domain and range can be difficult, but I think finding the domain and range of an inverse function is one of the easiest things that you can do in math. Because by definition, it's just, once again, switch the x and the y, switch the domain and the range. Don't even think about it. So that is, I think that's justifying why there's no left side to this graph. Right? While the inverse function is x squared plus 3, which is this. By definition, it can only be this. Am I doing that right? On the right side?
I think it's this side. Yeah.
Awesome. See, all right. So interesting. Okay. Interesting. Should we leave 2 as an exercise?
Oh, yes. 2 is a really good exercise. I think it would be interesting to think about the asymptotes, though, and how the asymptotes would get reversed.
Mm-hmm. Well, so like, if the asymptote is x equals, let's get the asymptotes.
So the asymptote, we have x equals 2, right? Because that would make our denominator undefined.
Mm-hmm.
And then since we have the plus 5, that means we have a vertical translation. So we're going up 5. So that means that y equals 5 is another asymptote.
So let me just add. You said that it's undefined. When a graph is undefined, that's where its vertical asymptote is.
Mm-hmm.
Cool. Because like what I thought about in my head was we have the asymptotes at x equals 0 and y equals 0, and we got a transformation happening. It's getting shifted to, then it's getting shifted up. You said shifted on the second one, but I just wanted to add that little extra bit. That the transformations are in our pocket right now. Let's use it. All right, so the asymptotes you said are x equals 2 and y equals 5. What do you think the asymptotes of the inverse function are going to be?
When we change our colors, because that's helpful, we'll have y equals 2 and x equals 5 as our asymptotes for our inverse function.
Yeah, it's simply switchy. Right, y equals 2 and x equals 5. 1, 2, 3, 4, 5. Right, and those are reflections of the line y equals x as well. You can reflect lines over lines. This is hopefully some review from geometry. Sweet. So we'll leave the actual function and the graphing to you guys. But there's a little nudge. Let's get to this last concept. What's the inverse of x squared? There's a red flag here. Let me raise it.
That is a red flag.
What is that red flag?
Because x squared is not 1-to-1. It's like our first example of a not 1-to-1 function.
So our definition said inverse functions must be 1-to-1. Functions that have inverses must be 1-to-1. All right, let's see why this is why must functions that are not 1-to-1 not have an inverse. Let's graph this real quick. What's the domain and range of x squared, by the way?
Domain is all real numbers. The range is non-negative reals.
For you.
All right.
All right, I'm gonna graph it real quick. Boom, 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 boom. I don't know why I'm going in the order I did, but I did.
You're alluding to something in the future.
Boom. Cool. All right. Switchy time.
Okay.
If I switchy, what's the domain and range?
We have x equals y squared. So then square root of that, we get, and then we're doing the principal root, right? So then we have y equals root x.
So if we do this, we're going to get f inverse of x is equal to x, the square root of x, right?
Mm-hmm.
But before we do that, let's just switch the x's and y's.
Okay. So we get 0, 0.
Okay.
We get, oh, should we change colors?
Yeah, we can.
So we get 0, 0. We get, oh my goodness, we get 1, 1, and 1, -1. This is not 1-to-1.
This is not
function.
Right. And there's the buzzword, right? This is not a function. If we just switchy, we are not going to get a function. So we need to do something about this, right? According to the work that you did a second ago, and it's totally where our heads are, right here. This work that you did earlier, the answer should be the square root of x, and this is not the square root of x. We need to do something.
Well, remember that we were talking about that the domain and the range, those switch.
Okay.
But then how can we make it so that we do have a 1-to-1 function?
So I think the solution to that problem is let's make it a 1-to-1 function.
Make it so.
Make it so. Let's take the function x squared and make it 1-to-1. Then we can take an inverse. All right? But I challenge you to make it 1-to-1, but to preserve the range. Our goal is to take the domain, the range back to the domain. So if we get rid of range values, then those values can't go back. So keep the same range, but change the domain so that we're not going back to two things. How do you want to change this function so it is 1-to-1?
Well,
I'm going to graph it real quick.
Oh, nice.
And then I'll let you tell me what to do.
Well, I think like I want to get out the root x that we were doing at the top of the page.
Mm-hmm.
That's because I think I've been indoctrinated into the convention of like this is what we do.
Mm-hmm.
But I think that it could be possible for every single student to have a different way of making this function one-to-one. There is an infinite number of possibilities.
Okay. So but your heart, your soul says you want the final answer to be the square root of x.
I want to be lazy and just write and just draw one easy thing.
Yeah. So let's do that. I'm totally on that boat. Let's get rid of that. We have.
Oh yeah, lovely. Look at that. So easy.
We've restricted the domain.
Yeah, the restricted domain here is from 0 to infinity, and the range is also from 0 to infinity, both including 0.
Let me scroll up.
So then when we do our reflection, we're just getting the square root function, whose domain and range are the same from 0 to infinity. Wow, you're doing the colors opposite now.
I know. I'm sorry.
Wow, lovely. And that was so easy to graph. It was just one continuous segment, or one continuous curve.
And that's kind of the essence of inverse functions. Is it must be one-to-one. If it's one-to-one, we're golden. We just do everything that you summarized earlier. It's not one-to-one, and we want an inverse. I mean, there are going to be reasons why we want an inverse. You might be able to think of some just off the top of your head. But we're going to want an inverse of non-one-to-one functions. So what do? We make it so. And we can make it so in many different ways. I think a fun way to do it would be to do it like this.
And those are some open circles that you got there, right?
Yeah, they should be. Let's make this one. Oh, let's make this one open. All right. That is one, and then it needs to keep going. They can't stop at 9, otherwise we do not preserve the range.
Wow.
That's one-to-one. But
one-to-one.
That's a ridiculous way to make it one-to-one. And then the inverse function is going to be very bizarre. I think the most reasonable way to make this function one-to-one is to keep the positive value. And actually, that is conventionally what we do. For the square root function, for x squared, by convention, we keep the positive domain. Right? But you could just as easily keep the negative domain.
Or any kind of hodgepodge that you want to do.
Yeah. There's some fun examples in the classwork, like the step function. How do you restrict the step function so it's one-to-one? But we'll leave that for you guys for the classwork assignment. I think we're done here. We've talked a lot about inverses, and I think the next thing is to just jump in and do some practice problems in class.
Sounds good.
Can I be a little bit reflective? At the beginning of the lesson, you asked me to be more cognizant of giving you the floor. How did I do?
I think it was better. And so that's good. I think that we can always do better.
Okay.
And I think seeking to always do better and also solicit feedback is a good place to be.
And I appreciate the feedback. I can do better. And I'll keep striving to do better. Because I care about you. And I don't want to, overshadow you. It's just not cool. All right. How do you want to finish this one?
I don't know. I think we should just close it out with a crummy sops because we haven't done that in a while.
A crummy sops?
Yeah, you just say crummy sops.
Oh, wait, I'm going to beatbox and you say crummy sops over it. Ready?
It's like cutting in and out though. It's not like
that's just funny. All right, here we go.
Daddy, look, my name is Philip. I am a poet. Wrote this poem just to show it. And I just turned 9. You can write rhymes, but you can't write mine.